Welcome back to the next video, everybody. Today, we are going to start chapter 7 of my notes, which loosely follows, among other things, chapter 7 of Cornell Silverman Stevens. This chapter is on Sayre's conjecture. I'm going to give an introduction to some of the background needed to understand what's going on. In the next video, I'll give more of an introduction to the actual topic itself. But our goal is motivated by the following observation: Ribot's level lowering theorem, which was a result that we used, which is crucial in the proof of Fermat's last theorem, is a special case of a much larger framework called Sayre's conjecture. In this chapter, I'm going to explain the conjecture, and I'm going to explain the special cases of it that we need for Weyl's proof. Now, this conjecture was solved in full in 2008 in a paper called Sayre's modularity conjecture. And then Sayre himself showed in his degree 2 representations paper, which I'll call SRM from here on out, that the modularity theorem actually follows from his conjecture. And so there is another alternate proof of Fermat's last theorem out there if you believe Sayre's conjecture. Okay, but we won't go through that proof. All right, so what do you need to get into this? First of all, you need to know a little bit about generalized elliptic curves. Let's let n be an integer at least 1, and let's let k be an integer. And let's let R be a z adjoint 1 over n algebra. So I want to be able to invert n. Denote by gamma sub 1 of nr the category whose objects are pairs E over S over R comma alpha, where S is an R scheme, so it's a scheme equipped with a structure map to R. And E over S is what we call a generalized elliptic curve. See chapter 17 of my notes far in the future, but you're probably going to also just have to consult Deligne-Rappaport or Katz-Maser at some point if you want to learn more about this stuff. Well, how should you think of an elliptic curve? It's like an elliptic curve over a scheme. Okay, and like the fibers of points are elliptic curves, or what we call n-gons. Again, more on this in chapter 17. Just think it's an elliptic curve over a scheme instead of over a field or something like that. Okay, and then what is this alpha? You want an embedding of group schemes alpha from this constant scheme z mod n z s to the n torsion of E, such that the image of alpha meets all irreducible components of all geometric fibers of E over S. That's a technical condition. But what I always have in mind here is, like, for ordinary elliptic curves, the n torsion of E is isomorphic abstractly as groups to z mod n z squared. That's kind of what's going on here. We're generalizing that. What's a geometric fiber of a scheme, by the way? Well, okay, so I have the structure map, E to S, right? Then I can take like points here. I can look at their residue field and take its closure. These fiber products are the geometric fibers, okay? This is a category, though, so I need to tell you what the morphisms are. I told you what the objects are. What are the morphisms? A morphism from E prime over S prime over R alpha prime to E over S over R alpha in this category is a Cartesian square. So it's basically a Cartesian square respecting structure maps. So we want E to E prime to S to be the same as E to S prime to S. But we also want to make sure that these diagrams are compatible with alpha and alpha prime in the obvious sense, which I'll let you think about. Okay, so I want to use this description to tell you what a modular form is in a more general setting than you're probably used to. A modular form, F of level n and weight k over R, is a rule that assigns to every object E over S over R alpha in gamma 1 and R an element F of E over S over R alpha in like the S sections of this sheaf omega tensored k times of E over S. What is going on here? Okay, first, I really just have to tell you what omega of E over S is, right? Then you tensor it k times, you look at S sections. Okay, it's the OS module defined by the pullback of the sheaf of differentials of E over S by the zero section in ES. The point is you have a group law which admits a zero section, which is a map S to E going the other way, okay? You have a sheaf of differentials here, pull it back along this zero section, that's what omega E over S is. Then take the tensor power k times and look at S sections. Okay, and then there's a technical condition which I'll let you think about. I want this assignment to be compatible with the morphisms in the category as well. And I mean, I'll let you think about what that means. Okay, so this is kind of, if you've ever looked at modular forms from a modular curves perspective, and we did a little bit in chapter 3, you remember that in general, like, modular forms can correspond to sections, global sections of the sheaf of differentials on the modular curve. This is kind of a generalization of that. Okay, so I'm going to denote suggestively by M of nk sub r the R module of modular forms of level n and weight k over R. This is notation we're used to from chapter 3. Okay, kind of a messy slide, but just bear with me. This will come to light kind of next slide. Look at the ring of formal power series over Z and Q. Then there's a Tate curve, Tate of Q, which comes with the basis dt over t of omega of Tate of Q over this ring of power series. There's an isomorphism of groups from z mod nz squared to the, okay, so what am I doing here? I'm going to take the field of Laurent series, formal Laurent series in Q and take the closure. I'm going to look at those points in Tate of Q. There's an isomorphism as groups with z mod nz squared. Here's the map, actually. You send AB to zeta to the A sub n times Q to the 1 over n to the B, where zeta sub n in Q bar star is just a fixed primitive nth root of unity. That's it. Okay. Now, if R is a Z adjoin 1 over n zeta sub n algebra, so I want to be able to invert n, but I want the roots of unity around. There's the usual Q expansion map from M of nk sub r to R adjoin Q to rings of formal power series over R and Q. It just sends F to this Fourier expansion, sum n greater than or equal to 0, a sub n of f q to the n. Oh, perfect. And the series is defined in the following way. You can take F and evaluate it at the Tate curve of Q and the map that sends 1 to zeta sub n, that to be this series times dt over t to the k. Okay, and actually this map is injective, thank God. So 2 different series here will correspond to 2 different Fs. Okay, so let's think of M of nkr in another way. There's another way of thinking about this or defining it. You can replace the term generalized elliptic curve in the definition I just gave you with just elliptic curve. And then you can demand that Q expansions obtained from all points of order n in the Tate curve over Z adjoin zeta sub n, formal Laurent series with coefficients in Z adjoin zeta sub n in the variable Q to the 1 over n be actual power series in Q to the 1 over n. This is kind of the way I prefer to think about it. Well, I kind of like both ways actually, but okay. Let's see. How about cusp forms? Denote by S of nkr the subspace of cusp forms. So that's the space of elements F of M of nkr with A sub 0 of F equals 0, as you might expect. These are just the modular forms which vanish on the so-called degenerate elliptic curves, which are those curves whose full Weierstrass models, given by the usual Weierstrass equation projectivized over R, have right-hand sides with non-distinct roots. Okay. The upshot of all this is you should think, you should just think of modular forms over R as the usual Q expansions with R coefficients, to be perfectly honest with you. Okay. But it's this theory above that lets you think of them that way. It's like the injectivity of this map that lets you do that, right? Okay. How about, do we have things like Hecke operators and also, like, does this generalized construction agree with our more specific constructions from chapter 3? Yes, when R equals C, M of nkc is just naturally isomorphic to the familiar space of modular forms on the upper half plane that we described and that we've been using for a while in chapter 3. Hecke and diamond operators, T sub n and diamond of A for A and Z mod nz cross for these new spaces of generalized modular forms can also be defined in ways that agree with our classical constructions from chapter 3. And then, of course, we still have the notion of Hecke eigenforms. For example, because I can still write modular forms in terms of Q expansions, I still have the identity A1 of T sub n of F is just A sub n of F. If F has Fourier coefficients, A sub n of F is an eigenform for all Hecke operators, T sub n. Okay. So all of the usual expressions we had when we were working in the complex case still hold formally in the general R case. Okay, perfect. Do we still have character spaces? Yes. If epsilon is a character of Z mod nz cross with values in R cross, let's denote by M of nk epsilon R the R submodule of M of nk R that consists of elements F such that diamond A of F is epsilon of AF for all A in Z mod nz cross. This is just the usual definition, right? This is just the usual definition of the character spaces. We say F is of type nk epsilon in this case. If R is a field and F in M of nkr is a non-zero Hecke eigenform for all the Hecke operators T sub n, then there's a unique character epsilon such that F is of type nk epsilon. You can't have more than one character, just like you couldn't before, right? I'll end this video by giving you some references. In addition to Deline Rappaport's paper, and also Katz-Mazur's arithmetic moduli of elliptic curves. You should also see Katz p-adic properties of modular schemes and modular forms, which is found in modular functions of one variable 3. You'll find much more information there on the definition of modular forms in this abstract setting. So next time I will introduce Sayre's conjecture and I'll give you a little bit of background and terminology. So that'll be next week. So I'll see you then. And thanks for watching.